This is Module 9, Lesson 2. We are going to add on now to what we already know about moles. In the previous lesson, we learned about moles and particles. So today we're going to relate moles to mass and volume. So first of all, molar mass. It's the mass of 1 mole of a substance. The way that we come up with these numbers right here is using the periodic table. So if we use, I don't have my pen selected. If we use the periodic table and we look at the square for carbon, we'll see the atomic number in the top, and then at the bottom we have what is the atomic mass of carbon. It says 12.01. Well, what we're going to do is we're just going to simply put grams on the end of it for a whole mole of carbon atoms. So this is not in grams on the periodic table, but we're going to switch it to grams to make the molar mass. Now, different teachers are going to tell you to round to different places. For the purposes of our class, I want you to round it to 1 decimal place. So very important, we're going to round it to 1 decimal place, because if we don't, then you and I are going to come up with different answers for everything. And since you're taking your test and quizzes in Canvas, it's going to be based on math that I've done using 1 decimal place for the molar masses. If you use 2 or you round it to a whole number, you're not going to get the answer right. So how I came up with 12.0 for carbon was I took 12.01 and I just rounded it to 1 decimal place. So 1 mole of carbon atoms would have a mass of 12 grams. If you look at the one for sodium, what it says in sodiums is 22.99. That's what it says as the molar, as for the atomic mass of sodium. So for the molar mass, we're rounding it to 1 decimal place. The 9 would round that one up, which would round that one up, so that's 23.0 grams for 1 mole of sodium atoms. For iron, it's the same deal. For Fe, the periodic table says 55.85. and that's going to round up to 55.9. Somehow I do that and don't know how I'm doing it. So anyway, round that up to a 9. We get 1 mole of iron is 55.9 grams. So what do you do if you have a compound? Well, you multiply. You do the math. So 1 mole of H2 would have a mole of 2 grams because there's 2 atoms of H, so it's 2 times 1.0. 1.0 for 1 atom of H, and we have 2 of them. For water, then it's 2 times 1 for the H's, and then it's 16 for the O. You add those together and you'll come up with 18 grams. What about NaCl? Well, it's 23.0 for the Na and it's 35.5 for the Cl. And so we end up with 58.5. All right. So what I have for you now is I have some practice. If you're looking at the practice sheet for this lesson, there is some practice on there. What I'm going to ask you to do is pause the video and work the first 7 problems. Come up with those molar masses, because once you unpause the video, I'm immediately going to give you the answers to those first 7 problems. Now, why am I doing it this way? Because I want you to be able to get the molar masses right to do the next step. So I'm going to go ahead and give you the answers for those. So go ahead and pause, try 1 through 7, and then check back in just a second. So pause it. Now, if you've already done this, I'm getting ready to write the answers. So here's what I came up with for KMNO4, and hopefully I did all of these correctly in my haste to get this done. This one would have a mass of 158.0 grams. KCl would be 74.6 grams for a mole. NH3PO4 would be 149.0 grams. The next one would be 262.0, 28.0 for carbon monoxide. This big ugly one here would be 310.8, and the really big one on the bottom is not quite as big as the last one, is 294.0. Now, if I made a mistake on one of those because literally I flew through them, then, ask me a question. Hopefully everything is okay moving forward. What we're going to do next is we're now going to apply this, and your notes tell you to stop at this point and go back to the video, because now what we're going to do is the follow me section about how to use this in conversions. So for example, we can take what we just learned and we can apply it to these conversion problems. If we have 65.2 grams of iron and we want to convert that to how many moles, we can do a whole new mole problem. Grams of Fe would go down here on the bottom, and we can relate grams to moles. How? By doing the molar mass. If you use the reference table, you should come up with 55.9 grams of iron in a mole. Again, I ask you to round it to 1 decimal place. If we do our math, the calculator is going to say 1.663 and then a bunch more digits. Does this count in our sig figs? No, it does not. This is something that everyone would agree upon or could come up with. So I go back to my original. This has 3 sig figs, so I can keep the first 3 digits. So that's going to be 1.17, oops, not grams, moles of Fe. And see, I kept myself from making a mistake by looking over here. Grams and Fe canceled. This is what my answer is going to be in. So you can do the same thing there. Catch yourself by using this. 1.17 moles of Fe. All right, the next problem. How many grams are in this many moles? Oops, somehow I've lost my penmanship here. 5.5 moles of NaCl. How would we do this one? We'll make your table. We know that whatever's up here has to go in the bottom of the next one. And we can go to grams because we know that we have a relationship between moles and grams. 1 mole of any substance is its mass using the reference table. So the mass of sodium is going to be 23.0 and the mass of chlorine is 35.5 using our reference table. That adds up to 58.5. So 5.5 times 58.5 is equal to 321.75. Can I keep all of that? No, of course not. These have canceled. These have an infinite number of sig figs, so it's just down to this one. 2 sig figs right here. It means I can keep the 3 and the 2. Don't you dare call this 32 because we have to keep our place value. So it'll be 320 grams of NaCl. There is our answer to this particular problem. Okay. And the last but not least, what about this one? How many moles are in 37 grams of Cl2? So start with what we know. 37 grams of Cl2. Okay. We're going to put grams of Cl2 down here on the bottom. Moles of Cl2 go up here on the top. Okay, now we know that we can use a reference table to figure out how many grams of anything are in 1 mole. Well, if we look at the reference table, Cl has a mass of 35.5. I've already rounded it to 1 decimal place, but this is Cl2, so we need to double that. That would be 71.0. I'm just doing the math up here. You do not have to show me the work. I'm doing it for your sake if you don't know how I'm coming up with this. Grams and Cl2 cancels, and now I'm left to do some work here. So once I put it into my calculator, I get 0.5211 and a bunch more digits. Can I keep all that? Never. Look back at the original number. I can keep the first 2 digits. So that's going to be 0.52 moles of Cl2. Now, before we go any further, it is practice time, but before we go any further, I'm going to go ahead and mention this about the Cl2. We have 7 elements on our reference table that exist diatomically. Di means 2. They exist as 2 atoms. So some of you at this point will look at this and go, well, why isn't it just Cl? I don't understand. Why isn't it just regular old Cl up there instead of Cl2? Because we have 7 elements, and how I remember this is I spell out a little saying, Brinkelhoff. Brinkelhoff stands for bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Brinkelhoff are the diatomic elements. So Cl2 is a part of Brinkelhoff right here. That is why it is Cl2. So if I ask this in words, I would just say 37 grams of chlorine and count on the fact that you know that chlorine would not be written as Cl, but it would be written as Cl2. So this is going to come into play in the future. This is not the last time you are going to hear this. Repetition never killed anyone. So we're going to start repeating it now, and by the time that I'm counting on you knowing it, hopefully it'll already be ingrained in your memory. So, now we have another relationship here. And what I have asked you to do in your notes is, like, if you want to, you can go ahead and stop and do those problems. And if you do, then you need to stop and go back to the video for this part of the lesson, or you can do all of the problems at once. The next relationship that we have is the volume mole relationship. Somebody, his name was Avogadro, had figured out that that a mole of any gas at STP, standard temp and pressure is STP, that is 0 degrees Celsius and 101.3 kilopascal. So this is basically freezing and sea level air pressure. If you have any gas at freezing and sea level air pressure, they will all have a volume of 22.4 liters. Now, we could go into an explanation as to why this is true. I'm highly doubtful that you even care. This relationship is on the very first page of your reference table. It's right down from the top. There's a little thing on there that gives you the number of a mole, which is also called Avogadro's number. And it says standard pressure. It tells you standard temp. And then it tells you that the volume of 1 mole of any gas at STP is 22.4 liters. So what that means is we can make a new conversion factor. 1 mole is 22.4 liters, or 22.4 liters is 1 mole. So I have some follow me problems. If you'll turn over to the back of your page, you have these on there. What can we do with this? Well, 35.2 liters of CO. And you're just going to trust that it's a gas unless it tells you otherwise if you're asked these questions. So how can I do this? Well, liters of CO has to go on the bottom. We know this by now because that's the only way for it to possibly cancel out. Well, we also know that there's 22.4 liters of 1 mole. So if you do your math, you are going to come up with 1.57 and a bunch more numbers. Actually, I need to put that next one on there so we can round. 1.571 and then some other digits. So this has 3 sig figs. This has an infinite number. As you can see, our pattern here is we always go back to the first for our sig figs. We keep the first 3. So that's going to be 1.57 right here. This is canceled. So we're left with this, moles of CO. There's our answer. Okay, let's try another one. How many liters are in this many moles of oxygen? So 5.5 moles of O2. Okay, so remember Brinkelhoff? This is part of what's Brinkelhoffed. So it's given to us as O2. We're going to put moles of O2 in the bottom, and we can go to liters. We're going to know I can relate moles to liters. There are 22.4 liters. It doesn't matter that it's O2. It doesn't matter what it is. 22.4 liters of any gas is 1 mole. So now when we do this one, and we do 5.5 times 22.4, we get 123.2. Can I keep all of that? No, of course not. These have canceled. This has 2 sig figs. I can keep the first 2 digits. They still have to be, the 1 still has to be in the hundreds place, the 2 has to still be in the tens place, so that'll be 120 liters of O2. There's our answer for the second one. And last but not least, how many moles are in, somehow I switch off my pen sometimes. How many moles are in this many liters of this one? So 68.36 liters of Cl2. Again, this one's Brinkelhoff, which is why it's written as Cl2. It's not going to change this problem. It's only going to affect molar mass. So we're going to have liters of Cl2 in the bottom, so they cancel, and moles of Cl2 on top. How do we know what goes here? Because we're going to have to memorize that 1 mole has a volume of 22.4 liters. Liters of Cl2 cancels, and I can do my math at this point. So we've got 68.36 divided by 22.4 is 3.0517 dot dot dot. You know, your calculator goes on for a while. Can I keep all this? No. I have to go back to this. This has 4 sig figs, so I can keep the first 4 digits. Well, that's going to be 3.052. The 7's going to round us up. And what's the words that go with it? Moles and Cl2. Okay. One more thing that we can do with these conversion problems using volume is we can actually use density as one of our conversion factors. If you have a solid substance or a liquid instead of a gas, you cannot use the 22.4 liters per mole. So the way those problems will look is they'll look like this. If the density of propanol is 0.828 grams per milliliter, and you have a sample with a mass of 14.5 grams, what's the volume? You have these on your paper as a couple of follow me examples here that you could do with me. So most of my students have trouble deciding whether or not to use this number first or this number first. And so usually what I ask them to do is to kind of look at what you're given. And so they're giving you the density. And then if you took this part of it right here, and you took it off, and you have a sample has a mass of 14.5 grams, what is the volume? This would be the extra information. This little if part of it would be the extra info needed to solve the problem. Usually we're not converting things that have 2 units in them, so the 14.5 is where we're going to start. 14.5 grams. And let's see, it's a propanol. I'm not going to write that in here. We'll just leave it at 14.5 grams. Grams is going to go on the bottom, and it wants to know the volume. So do I know anything that would relate the volume, like milliliters, to grams? I do. It's this density right here. So another way to write this is to write it as 0.828 grams per milliliter. I mean, it's an understood 1 milliliter on the bottom here. So if we do that, I could flip it over. If I put the 0.828 in the bottom and the milliliter on top, then I have a fraction that I can use to do my conversions with. I've got 14.5 divided by 0.828, and I will end up with 17.512 dot dot dot, you know, so on and so forth. So how do I do this? Well, the grams has canceled. I'm left with milliliters. What about sig figs? This portion of it right here still has an infinite number of sig figs. This right here has 3. So I get to keep the first 3 digits. So it'll be 17.5 milliliters as my answer. Okay? I have another follow me problem. Now this one I messed up a little bit, and I realize it now, but it's already done, like you already have it in your problems. This was just simply asking you for the density in grams per milliliter of a substance that has a mass of this and a volume of this. Well, I don't have it's not really a conversion problem per se using density. We are going to have to do a little converting. It tells me right here that I want to end up with grams over milliliters. Well, I have milliliters right here, but this is in kilograms. So the only conversion part of this, and it's the part where I kind of messed up, is converting kilograms to grams. So kilograms goes in the bottom, grams goes on the top, and we know that 1 kilogram is 1,000 grams. So if we do that conversion, that's 987 grams, and then all we need to do is divide it by, that would be 452, is the same thing as 4.52 times 10 to the second milliliters. So if we do that, that's all that's required of this one, is just simply doing the math of it. That's 2.183 dot dot dot. So how many sig figs do I put in my answer? We'll go back to these. This has 3 and this has 3. So let's keep the first 3. So that will be 2.18. Neither one of these cancels, so that would be grams per milliliter. So I messed up a little bit with that one, but it works out okay in the end as far as reviewing some conversions. And then I have one last density conversion for you. It says the density of ethanol is this. How much in grams does this many liters mass or weigh is kind of the way a lot of people would say it. What's the mass of this many liters? So which one of these two numbers do I use? Well, here's the question. How much in grams is this? So I start with the thing it's asking me about, which is this. The 9.85 times 10 to the negative second liters. Liters will go on the bottom. Do I know anything to get me to how much in grams? I do, but this is grams per milliliter. So I need to put milliliters on top and liters on the bottom. It takes 1,000 milliliters to make 1 liter. And then this is going to have another step to it. Liters would cancel. Milliliters can go in the bottom. Remember when we did multi-steps, whatever was up here goes down into the next one? And then I can relate the grams to milliliters. This is 0.802 grams per milliliter. So now we're going to do our math. We've got this number times 1,000 times 0.802. So my calculator says that is 78.997. Okay, as far as sig figs goes, I'm still going back to my original. That's 3. So I get to keep the 7, the 8, and the 9. Next to it is another 9, so that's going to round me up to 79.0. Liters canceled, milliliters canceled, grams is what's left, so that's the unit of my answer. Okay, now you have more practice problems that you can do. So what you need to do is you need to go to your sheet and you can practice these. So you could have either done this in, segments where you do a little bit, watch more, do a little bit, watch more, or you can now do all of them together, however that happened.